Who is more likely to get a medical checkup, employed or unemployed people? A team of physicians and public health specialists collected data on a sample of 2,200 individuals. The results are in the table below. Run a hypothesis test to determine if there's enough evidence to prove that a higher percentage of unemployed people have routine medical checkups than do employed people. We saw that there was strong evidence in the confidence interval that the difference between these population percentages was negative, indicating that the percentage of unemployed people that have routine medical checkups was greater than the percentage of employed people that have routine medical checkups. So what we want to show is that the population 2 percentage, the percentage of unemployed people that have routine medical checkups, is greater than the population 1 percentage of employed people that have routine medical checkups. So I want to show that the difference between these two population percentages is less than 0. In other words, it's negative. What I will assume is just the opposite, that this difference in percentages is greater than or equal to 0, or as we normally do, just say equal to 0. Certainly if I can show the percentage is less than 0, I'm proving that it's not greater than 0. And setting up the sampling distribution here for the difference in sample percentages, I'm going to be centering that at 0, assuming that the null hypothesis is true, and see if our sample data agrees with it, basically. This is going to be a lower tail test. My endpoint for my rejection region will be a negative 1.645 standard units to the left of center, or 0. Now, to get the standard deviation of the sampling distribution, I have to pool the sample percentages. Again, when you're building the sampling distribution, you're assuming that the null is true. And if the null is true, and there's no difference in the population percentages, then the sample percentages are estimates of the same thing. And therefore, instead of using them individually, we will average them together and then use that as the percentage. So averaging them is also based on sample size. So we'll take a weighted mean, which we'll call p hat. And my formula for that is N1, my first sample percentage, and N sub 2 times the sample percentage from population 2, and then divided by the total sum of the sample sizes. Now when I do that and put the values in, I get 1,140 times 0.563 plus 1,106 times 0.669, and then divided by the total of the sample sizes, 1,140 and 1,106. And this gives me 0.6152. And then I'm going to use that in my standard deviation formula. So there's a two-step process in calculating the standard deviation of the sampling distribution. So 0.6152 times 1 minus 0.6152 times 1 over 1,140 plus 1 over 1,106. And then calculating this, I get 0.0205. So just to get the standard deviation of the sampling distribution, I have a two-step process. In some ways similar to doing the t-distribution for means when you have two populations. Very similar type of process. Okay, proceeding then, I have my rejection rule. I'm going to reject h sub 0 if z is less than negative 1.6 1.645, actually less than or equal to negative 1.645. And then Z is my test statistic. It's based on my sample, and my sample difference is 0.563 subtract 0.669, and then I'm testing against 0, which we normally do when we're comparing two populations, and then divided by my standard deviation 0.0205, and I get a negative 5.17. And negative 5.17 is so far to the left of negative 1.645, I'm going to reject H sub 0, since negative 5.17 is less than negative 1.645. And actually, I am so far to the left of that, I am off the chart. I'm beyond 3 standard deviations of the center, and I'm in outlier territory. As a matter of fact, when I go to the table, it's off the chart. And basically, I can say that the p-value is equal to 0. Now, if I go ahead and put this into Excel, you will get a very small p-value. But rounding it in any fashion, it's going to be practically 0. So regardless, I'm going to reject the null hypothesis. And what I have proven then, I have statistical proof that the percentage of unemployed people that have routine medical checkups is greater. So, as always, a hypothesis test is setting up the null and alternative hypotheses. The alternative hypothesis is, in some sense, what you're looking to prove. Usually, your data supports the alternative hypothesis, and the question is whether that sample evidence, your data, is strong enough to reject the null hypothesis. The step 2 is the sampling distribution, and that's assuming that the null is true. It's built on that. And then when we get to our test statistic, do those two agree? And they, in this case, don't. The data that was collected gives an estimate of the difference that is so far away from 0 that it's an outlier and really off the chart. So yeah, the test statistic does not agree with the sampling distribution, and therefore we're going to say that the null is wrong. So we have support of the alternative hypothesis, that the difference is less than 0, which means that population 2 percentage is greater, or that the percentage of unemployed people that have routine medical checkups is greater or higher.